Hi and welcome to another episode of the programming series. Today in this video we'll discuss recursion, arguably one of the important topics in programming. We'll walk through some examples together and I hope this video provides you some valuable insights. Now let's begin our journey. It's one of our beloved characters, Senku. He's in the 4th grade, but he's exceptionally smart and passionate about science and technology. One day, Senku decided to build a small rocket because of his lifelong dream of going to space. Realizing that this project was too big to handle alone, he asked his friend Taiju to write a countdown program for the rocket launch. You're someone that Taiju always looks up to, therefore he asked for help. He's a wonderful kid, therefore you couldn't say no to him, and promised that you'd help him. Here is the code that Taiju came up with. I think we can agree that if a program indeed performs a countdown from 5 to 1, the code is functional and doesn't contain any errors, yet something about it feels inefficient. But let's think about this a bit more. What if Senku wanted to count down from 20? Let's pause for a moment and really think this through since we promised to help Taiju. But Taiju have to write 20 separate functions. What about 100? Writing 100 individual functions can be extremely tedious and inefficient. There must be a better way to achieve this. Let's analyze what Taiju has written and see how we can help him improve the code that he had written. Since we promised Taiju our help, let's explore how we can make his countdown code more efficient. There are a couple of key observations we can make about this code. Each function performs the same operation, printing a number with only the number itself changing. The function definitions are also very similar. They all have the same return type, that is void. They don't take any parameters, and the core logic within each function is almost identical. They only differ in the number itself being printed. With these observations, we can conclude that they are essentially the same operation being performed with the different input values. Before we move on, let's take a step back and refresh our understanding of how functions work in a program. To help visualize this, let's think each function as representing a single book. We're about to explore how this analogy can help us better understand what's going on. Imagine you are reading a book, perhaps a research paper or a programming article. Often these kinds of text include references, and understanding those references is essential for a complete understanding the full context. As we discussed earlier, some books may include numerous references. To fully grasp the content of the book that you are currently reading, it's often essential to read these reference resources first. So imagine you're reading book 1. Inside book 1, you find references to 3 more books, book 2, book 3, and book 4. So the question begins, since you have 3 references from book 1, how should you approach them? In which logical order should you read? Let's say you decided to read book 1, and on page 4 you see a reference to book 2. Later on page 20 it references book 3, and again it references book 4 on page 40. You have just reached page 4 of book 1, and so it mentioned the reference to book 2. You'd have 2 options here. The first one is that you could skip the reference and continue reading the book 1. However, this might make it harder for you to understand the content later. Another option may be you could take a break on page 4 of book 1 and read book 2 first. The second option, pausing at page 4 of book 1 to read book 2 first, seemed the best approach. Therefore, we have decided that whenever we encounter a reference to another book, we'll pause our current reading book, finish reading the reference book, and then return to where we left off to our original book. As we are now reading book 2, we should be aware that it might also have references, so complete understanding requires us to understand those references. We'll use the same approach for book 2 as we did for book 1. Whenever we encounter a reference to another book, we'll pause our current reading, finish the reference book, and then return to our original one. For example, if book 2 references book 5, we will pause book 2, read book 5, and upon completion of book 5, we would resume book 2 from where we left off. We begin with book 1, which references book 2 references book 3, and so on, up to book 6. Since book 6 contains no further references, we can complete it, and upon its completion, we could then return to book 5 and continue reading from where we left off. This process repeats for each book. We pause to read any reference books, and once those are complete, we finish the original book. We continue the cycle until we've read all the books. There might be tens or hundreds of books that we may have to pause so far to read reference books. How do we know that in each book we're supposed to return upon completion of a book? In the context of when we have hundreds of books, it becomes extremely difficult to keep track of everything. To avoid this problem, we decided to organize the books whenever we pause reading one to consult a reference. We stack the book in the order they were paused, with the first paused book at the bottom and the most recent on top. This way, we could easily resume reading by picking up the top book. Once a book was finished, no more references, we removed it from the stack and resumed the book beneath it. Our reading started with Book 1 since it contained a reference to Book 2. We paused Book 1 and started reading Book 2. While reading Book 2, we encountered a reference to Book 5. We then paused Book 2 and placed Book 2 on top of Book 1. We began reading Book 5. Let's say Book 5 has no references to other books. Once we finish Book 5, we can set it aside from the book arrangement. We can pause to Book 2 to read Book 5 as Book 2 referenced it. Now that we have finished Book 5, we have taken it out of our reading stack and marked it as completed. This leaves Book 2 at the top, so that is what we'll be reading next. Book 2 has 3 references. Midway through reading Book 2, we come across a reference to Book 5. We decided to read Book 5 before continuing with Book 2. Once we would finish Book 5, we went back to Book 2. We then encountered a reference to Book 6. Consequently, we paused Book 2 again to read Book 6. Since we are now reading Book 6, it should be placed at the top of the book arrangement. Book 6 was at the top of our reading list, so we started with it. Since it contained no references, we were able to read it straight through and mark it as complete. We then returned to Book 2 and continued reading from the last stopping point. We have finished Book 6, so we can mark it as complete and remove it from our reading stack. The book now at the top of this stack, the one directly below where Book 6 was, is our next book for reading. We return to Book 2, resuming where we left off before pausing Book 6. However, after only a few pages, we encountered a reference to Book 7, so we paused Book 2 again and began reading Book 7. Since Book 7 is the one that we're currently reading, we placed it at the top of the book arrangement. If Book 7 has no references, we finish it and mark it complete. Then we move on to the book directly below it. If Book 7 does contain references, we pause our reading and read the reference material first, placing it at the top of the book arrangement. This process repeats step by step until we complete Book 1, which is the last book in the book arrangement. Let's reconstruct how we have organized our books. Our system was based on references. This arrangement would always place the reference book on the top of the book containing the reference. Whenever we encounter a reference within a book, we pause our current reading and begin reading the reference book. When retrieving a book from our book arrangement, we always took the topmost one. Books are read in a specific order, always starting with the one on the top of the book arrangement. When a book is finished, it's taken off the top. The next book directly below the one that we just removed becomes the new top book, and it will be the next one to read. This meant the newest book or the most recently read was always accessible on the top. Now that we have a grasp of this concept, we can now turn our attention to the call stack. For the purpose of understanding this concept, let's imagine that each book represents a function. Let's summarize the book example that we have discussed. Imagine its function is a book. Each book might reference another books that are essential for understanding its content. A logical approach would be to pause currently reading and consult a reference book. If the reference book also contains references, you pause again and read those books first. To keep track of your progress, you stack the books in order, the first book at the bottom and the most recently paused book at the top. This arrangement makes it easy to resume reading the current book by picking up the one on top. Once a book has no more references, you finish it, remove it from the stack, resuming the book beneath it. This stack makes it easy to remember which book to return to after finishing a reference. The top book on the stack is always the one we're currently reading. Once we finish a book, a function completes its execution, we remove it from the top of the stack, and the book that was previously below it becomes our new focus. Repeat this process until the stack is empty. So that's essentially how the call stack works. When you run a program, the operating system knows to begin execution at the main function. The very first line of code inside the main function's body is where the program's execution begins. Remember our book arrangement example? Well, when we call a function, it's like adding a new book to that arrangement. This arrangement for functions is called the call stack. It keeps track of the functions that are currently running. Within main function, instructions are executed sequentially, one line at a time. Remember our book example? Well, the main function is like that the first book what we started reading. We read a book sequentially from page 1 to page 2 and so on, just as we don't jump to page 20 of a book without first reading the earlier pages. A function is executed sequentially. Its line of the code is processed one after the other, step by step, without skipping ahead. Let's say you're reading a book and you come across a reference to another book. You don't just ignore it, right? You'd probably pause your current reading, go find the referenced book, and read it. Function calls work in a similar way. When a function is executing and encounters a call to another function, it pauses its own execution, adds the new functions to the call stack. Think of this as a list of functions waiting to be finished, and it starts executing the called function. Once that function is done, it's removed from the call stack and we go back to where we were in the original function. Therefore, we pause the execution of the main function and begin executing function A. It's important to remember that the CPU always executes the functions at the top of the stack, much like how we read the book starting from the top. While executing function A, we encounter another function called function B. This is similar to when we were reading a book and came across a reference to another book. Just like with the book, we pause the execution of function A, add function B to the call stack, and then begin executing function B. Once again, while executing function B, we encounter another function called function C. We follow the same process. We pause the execution of the current function, function B, add function C to the call stack, and begin executing function C. Since function C is at the top of the stack, it is the function currently being executed. Any function beneath it on the call stack are temporarily paused, awaiting their turn. If we look at the function C, we see it doesn't contain any function calls. It's similar to when we are reading a book and there are no references to other books. Remember our example of reading a book? We consider a book complete not just when we reach the last page, but also when we have followed up on all the references mentioned within it. Once we've finished, we remove the book from the book arrangement. Now let's relate this to functions. Once a function completes, either by reaching a return statement or the end of its code, it is popped off or removed from the call stack. Execution then resumes in the calling function, similar to removing a finished book from the shelf or the returning to the previous one. We executed all the lines within function C, so we can say it has been fully executed. Now we remove it from the call stack and resume execution of the functions that were paused below it, continuing from where we left off. When we called function C from within function B, show the point where we pause execution of function B, specifically line 3 on the call stack. This allows us to return to function B and resume execution from line 3 once function C has finished. Function B's execution is considered complete when all its lines of the code have been executed or when a return statement is encountered. Once function B has finished executing all its lines, it's considered complete and is removed from the call stack. We then return to function A. Remember we saved the line number in function A, where we pause to execute function B. We now resume execution of function A from line 3. Now that the execution of function A is complete, we remove it from the call stack and resume executing the main function. Remember, we saved the point where we paused the main function, which was at line 3, so we can continue execution from that point onward. With all the lines in the main function executed, the main function is removed from the call stack. With the call stack now empty, we can conclude that the program has executed successfully. Congratulations, you have successfully executed the program. Now that we have all these informations, let's return to helping Taiju with an effective countdown program. Let's take another look at the observation we made about Taiju's code. There were a few key observations that we can make about this code. Its function performs the same operation, printing a number, with the number itself changing. The function definitions are also quite similar. They all share the same return type void, don't take any parameters, and the code logic inside its function is nearly identical. The only difference is the number being printed. From this observation, we can conclude that the functions are essentially performing the same operation but with the different output values. Based on these operations, we can conclude that we can create a more general countdown function. While this countdown code is more general than Taizu's original version, it still has a limitation. We now have a function that can print any given integer. However, to count down from 100, we need to make 100 separate function calls, each with the next number in the sequence. This approach works for small numbers like 1 through 5, but what happens when we want to count down from 100 or maybe 1000? Calling the function for every number quickly becomes unmanageable. This approach is simply not scalable, efficient, or practical. Let's pause for a moment to review what we are trying to achieve here. Our goal is to build a program that performs a countdown. It should begin at a specified number, decrement by 1 which is a state, and automatically halts when it reaches 0. With this information in mind, could we write a more general program? Since we're dealing with functions now, it makes sense to start with them in order to write a more optimized program. As we discussed earlier, we understand how the call stack works and how function calls are made. So let's consider how we can use this in our program or take advantage of it. What's bothering us right now is that we're manually calling each function, even if it is something we have to do 1,000 times. Let's think through this and see how we can use the call stack to solve the problem. Now let's think about how we can use the call stack in our current context. We know that during function execution, any new function call is placed onto the call stack. Can you exploit this behavior to our benefit? This code probably looks somewhat familiar. We have worked with similar examples, but notice something important. The countdown function takes an integer n, prints its value, reduces n by 1, and then calls countdown again with the new value. This is different from our earlier examples where we called distinct functions. We haven't seen this before. Usually we have been calling different functions, but this time it's the same function calling itself. Even though we are calling the same function repeatedly, so what? They're just like any other function calls and are treated in the same way by the call stack. Now let's walk through the execution of the countdown program step by step. The execution of every program starts at the main function. The program then proceeds sequentially, executing its line of the code within main inner. Since the main function is a function, it must be added to the call stack. Since the main function is the one currently executing, it is processed line by line. During this execution, we encounter a call to the countdown function with a value of 5 passed to it. The current execution of main is temporarily suspended. The countdown function with the value of 5 is pushed onto the call stack. The program's focus then switches to executing the instructions within the countdown function. Now we are executing the instruction within the countdown function. During this process, we encounter another function call to countdown with a value of 4 passed to it. Since countdown is a function, we add the countdown functions with the parameter 4 to the call stack and begin executing its instructions. Similarly, a countdown function with the parameter 4 is currently executing. During this process, another function call is encountered. A countdown function with the value 3. Following the same procedure, we add a new countdown function call initialized with the value 3 to the call stack, then its execution begins. Similarly, a countdown function with the parameter 3 is currently executing. It then encounters another function call, a countdown function with the parameter 2. Consequently, the execution of the function with the parameter 3 is suspended, and the execution of the countdown functions with the parameter 2 begins. The same step would then be followed for the countdown function with parameter 2. The same applies to the countdown function with parameter value 1. And it's the same thing again for the countdown function at 0. Hold on, it appears the countdown is continuing below 0. Is it not expected to terminate at 0? To this point, the countdown has functioned as expected, correctly reaching 0. However, it is not our intention for the countdown to proceed into negative. This was not part of our design specification. Our current process has revealed a further issue. Let us now focus on resolving this problem. It's important to remember that the call stack has a fixed size. If we continue to add functions calls onto it, we'll inevitably exhaust this space. Consequently, we will reach a state where it becomes impossible to push any more functions onto the call stack. Therefore, we must ask, was this problem encountering in our current implementation when it was absent in previous versions? The core issue with our current design is that we are continuously add functions to the call stack, which has a limited size, without ever removing them. However, our earlier implementation correctly managed the call stack by both adding function calls upon invocation and removing them upon completion. Before we proceed further, let's review when a function execution completes and when a function can be removed from the call stack. There are two main scenarios in which this happens. First, execution completes when it reaches the end of the code block, meaning there are no more instructions to execute. Second, function execution also concludes when a return statement is encountered. Neither of the conditions described above applies in our current countdown program. As a result, there is no process by which functions are removed from the call stack during execution. Consequently, the only action performed on the call stack is the continuous accommodation of new function calls. In our countdown program, we don't wish for the count to go below 0 or towards negative values. When the current count reaches 0, it's clear that we no longer need to make further function calls. Indeed, proceeding beyond 0 is contrary to our objective. Therefore, when the count reaches 0, instead of calling another function, we can simply execute a return statement. This return will ensure the removal of the current function from the call stack. It would lead to below paused functions of the call stack to reach end of the instructions, which indicate completion of function execution, and they are also be removed from a call stack. This action will allow the function below the current one in the call stack, which were previously paused, to continue and complete their execution. As this function reaches the end of its instructions, it will be removed from the call stack, signaling the completion of its execution. Alright, let's change our countdown program in a way we just discussed about. We'll use an if statement to check if we have reached a count of 0. If our if statement tells us we have reached 0, instead of calling the countdown function again, we'll just use a return statement. Let's walk through how our updated countdown program will run step by step. Imagine we're at a point where the current count is 0. For context, here is what our call stack looks like up to this point. Now, when we look at the code, we see that if statements will evaluate true because the current count is 0. As a result, the return statement inside the if block will execute. This return acts as a signal to the system telling it the function is complete, remove the functions from the call stack. Crucially, because we use return, we won't make any further countdown function calls, nor any instruction after the return statement would be executed. Since the countdown functions with a value of 0 has finished executions and has been removed from the call stack, the functions with a value of 1, which was temporarily suspended, will now resume execution. The execution starts from where it was paused at line 8. The execution continues from line 9 and it will keep running through its code until it reaches the very end of the countdown 1 function. Once countdown function with value 1 completes, it will be removed from the call stack and control will pass to the next function countdown with value 2. To further clarify this process, I will now play an animation that visually demonstrates the call stack along with the corresponding function calls. With the call stack now empty, we can confidently conclude that our countdown program has executed successfully. Let's take a look at the final version of our code. By leveraging the call stack and incorporating a simple conditional check, we have transformed our countdown into a robust and scalable solution. It can now seamlessly handle countdowns of any duration, whether it's 500,000 or even much larger numbers, all without redundant code. This example clearly demonstrates how the good understanding of the call stack allows us to write the code that is both elegant and highly reusable. And with that, congratulations, you have just implemented recursion. Alright, it's time to hand over the code to our excellent boy Taizu. Thank you for helping Senku realize his dream.